Hello everyone. So today we start a new block of lectures. So we'll talk about neural networks. So far we discussed optimization algorithms, so in other words, learning algorithms. And right now we will discuss a very specific class of models called neural networks, or sometimes referred to deep models or deep learning models. So before we start, we need to remember what is the objective functions, because in the end, the objective functions is what we optimize. And here we focus on likelihood-based learning. What does it mean? It means that we have observations. We have now observations as a pair of two quantities, an input, for instance, an image, X, and Y, an output, a class label or a stock price or whatever. Okay. And we have a model with parameters theta, and we'll think of it as a probability distribution, a conditional probability distribution of a label or an output for given input and parameters. And now, please remember this, because logistic regression and neural network, all of these models, they model exactly this quantity. And the log likelihood function is our objective. We assume IID. Please refer to previous lectures when we discuss it in more detail. So we consider the log likelihood functions as our objective. And of course, this is for maximization. If we are interested in minimization, so we of course put the negative sign. All right. So this is a quick recap about likelihood-based learning. And we will start our discussion about neural networks from logistic regression model, because as you will see, neural networks could be seen as stacking multiple logistic regressions on top of each other. All right. So what is the logistic regression? Let's take a look at a very common example from machine learning. Spam detection. All right, so we have a spam detector, and how it works. We represent a message, an email, using some words, okay, a bag of words, and we determine whether a specific word occurs or not in email. If it occurs, we assign 1, if not 0. So for instance, let's say that we look at four words like hello, find, mom, and call. And if an email contains these words, so then we assign 1. And our output is whether an email is a spam, it's 1 and it should be deleted, or not. So then it's 0. And our goal here is to provide probabilities of a spam, or just to classify messages, right? So these are more or less equivalent. And now how we can do it, how we can proceed, we can of course gather a lot of emails. We can manually, we can assign whether this is spam or a proper message. And then of course we train a model that takes this message represented by a bag of words and learn this mapping through the log likelihood function. And what is the logistic regression model? So let's say that this will be our spam detector, okay? So in general, it takes some x's, it produces either 0 or 1, and theta are some parameters real valued, and there are exactly the same number of these parameters as inputs. And we model y using Bernoulli distribution. So right now you see why we are discussing this tossing a coin problem, because this is exactly almost the same issue. So we are interested in modeling the probability of y as a Bernoulli distribution. And here we have two maybe new concepts. So first concept is sigmoid, and this is the sigmoid function. And we have also this theta times x written in a matrix notation. So this is like we assume that vectors are columns, and so transposition is that we take a column vector, we're going to represent it as a row vector, and we multiply it using matrix multiplication. So first theta is multiplied with the first x plus second theta multiplied with second x, and so on and so on. And how does sigmoid function? Why we use sigmoid function? So sigmoid function can model probabilities. Sigmoid function squashes everything between 0 and 1, with importantly 0.5 in the middle, okay, for 0. So now we can, so what we do right now is that we model the probability of a spam, or y equals 1, using sigmoid function and some parameters. So then how it will work, so then if some specific words occur for label equal 1, so then they should get some parameters that are larger, that will try to push this probability towards 1, okay? And this is how it works. Further, sigmoid function has very nice properties. So first of all, sigmoid is between 0 and 1. Second, the derivative of sigmoid is expressed by sigmoid itself. So it's sigmoid times 1 minus sigmoid. So it's very interesting. And another thing is that sigmoid of a negative value is equivalent to 1 minus sigmoid. So these are very nice properties, and they are very often used in machine learning. And in our model, of course, we have that probability of y equal 1 for given x is just sigmoid of this sum. And of course, the probability of 0 is simply 1 minus this sigmoid, right? So this is the property of probability. It must sum to 1. All right. So how we can represent it as a small small network, okay? Not neural network, but small network, okay? So let's say that we will define nodes as like here, that there are variables, inputs, and we sum it, and then we have output, probability distribution of applying sigmoid, right? So maybe a small comment here. Of course, right now we explicitly write that we sum, and we have the sigmoid, and we have, in edges we have parameters. And further on, we'll simplify a little bit this notation. But please keep it in mind that it's already a kind of a network, okay? Without some additional nodes, it's everything simply follows from inputs to outputs, okay? And all right, so how do we train it? Using gradient descent. So of course, to calculate, so to learn using gradient descent, we need to calculate gradients. And this slide is a little bit heavy, maybe mathematically heavy for some of you. However, I try to present it step by step. So if you have any trouble, so please do it by yourself and refer to slides and check, okay? So of course we are interested in calculating gradient of negative log likelihood function. So by assuming IID, we turn it into sum of logarithms. Then we plug in the Bernoulli distribution, and we apply logarithm to that. So we have y times logarithm of sigmoid function plus 1 minus y times log of, we should write here 1 minus sigmoid function. However, we use this property that 1 minus sigmoid function is equal to sigmoid of negative argument for simplicity. Then, of course, we need to, so we go with gradient inside, because the gradient of sum is sum of gradients. And we calculate gradients using these rules that we saw in previous slides. So, of course, here we have this more complicated gradient, because we need to calculate gradient of log. So log is 1 divided by something, and this is 1 divided by sigmoid, and then we calculate times gradient of sigmoid, and gradient of sigmoid is sigmoid times 1 minus sigmoid, and again we use the property that 1 minus sigmoid is sigmoid of negative argument. And then we go inside further to the sigmoid function, and this is a linear term, so theta times x, and gradient with respect to theta results with x's. And then, of course, we apply the same to the other side. And because we have sigmoid of negative arguments, so we have this minus sign here. All right, so now, of course, what we need to do, we need to simplify a little bit. Then we divide by, in the first part by sigmoid and the other part by sigmoid with negative argument. All right, we have something simpler. Now we need to simplify further. So of course we now multiply the second part. So negative minus sigmoid plus y times sigmoid x. We simplify further. We see that we can obtain something nicer. So this is just minus sum of y times x minus sigmoid times x. And as you can see, we can take x outside. Please remember from the right side, because this is matrix calculus. So on which side some quantity stays, it must stay on the same side. And in the end, we go with minus inside. So we see that this is sigmoid minus y times x. So this is our gradient, okay? Again, I went through that a little bit maybe fast. Please do it by yourself at home as a homework, okay? And verify whether all steps agree with these slides. And so to understand what's going on in the gradient. So if we have y equal 1 and sigmoid is really high and almost equal 1, we will have gradient equals 0. It means that we are correct. However, if sigmoid is 0 or close to 0 and y is 1, so then we will have a huge error, right? Sigmoid minus y will be close to 1, minus 1. So then we will have huge update. And vice versa. If y is 0 and we have sigmoid 1, we'll have huge update. If it's 0, so then we have no update. So now it's actually very interesting because we can see what is the gradient and we can understand what's going on here, right? And it makes a lot of sense. If you make a big error, just update your weights accordingly, right? So the update rule, the final update rule is very simple. So we just take gradient descent, we take our current weights, so parameters theta, we subtract, because we follow the opposite gradient direction, alpha, the step size, times sum over observations, and sigmoid minus label times x. But what, of course, if n is a large value, so we have thousands of images, for instance, or thousands of messages. It could be extremely slow. And here it's another very important and interesting concept. It's called mini batches, so stochastic gradient descent. So we assume that we just follow gradients with much smaller batches, okay? So now instead of taking all images or all messages, we just take a small subset of them, like 100, for instance, or 32 or 64 or so on, okay? And the most extreme case is, of course, when we just consider one single case at a time and we just make a lot of updates, right? A lot of updates, because we will update every time we see one image or one message. How it works? So to visualize it, so on the right we have how gradient descent performs. So this is some, let's say, quadratic function with minimum in 0. And when we take this gradient descent, so the gradient is approximated really well. So we go something like we follow these lines of steepest, direction. And of course, with stochastic gradient descent, now this update is, we don't see all images, or all access, all inputs, so we just see a subset of them. So it goes down, but with more steps. However, of course, now if we see what is the computational burden to calculate sum over thousands of images or 100 images, so of course stochastic gradient descent in practice it's faster, but also because it's more stochastic, so it turns out that it has even very nice properties that it can even achieve better results than just gradient descent. But theoretical parts aside, please remember this, that you can use mini batches because this is what we use in neural networks, okay? Because then updating the whole neural network for hundreds or thousands of objects, it's simply impossible. It will not fit your memory. All right. So this is the quick intro to logistic regression within something like 15 minutes we did. But now, of course, our interest is neural network, okay? And how we can think of neural networks. So what if we stack multiple logistic regressions? What if we say that instead of outputting the P of y, the probability of P of y, we will put something in the middle. We'll just apply these logistic regressions again. So we will do as follows. So we just have D inputs, and now we will have M additional logistic regressions in the middle, on top of which we will put another logistic regression that will output probabilities, all right? So now we have some additional set of weights that are called in neural networks. So we have thetas that they are responsible to create for us probabilities of outputs, but we have also a matrix of weights from access to these hidden states, hidden nodes H, denoted by H. All right, so far so good. So we don't see any issue here. We shouldn't see any issue. It's possible. It's our model. We can also represent it maybe in a more concise way that we just very often will just forget about these sum nodes because it's a little bit useless. Or we can even represent them as something like blocks, rectangles. Okay, so but this is just a notation issue, diagrams, nothing else. It's not maybe necessarily important. But what is important now, that what we get by stacking this all together, we of course we still model distribution of y as Bernoulli distribution. We just now express probability of y equal 1, we express it in a different way, a more complex way. So this is something like now we have, let's say that we go from input, we have x times w or w times x in matrix notation. So, and we apply sigmoid on top of that. These are, let's say, our hidden nodes, h, and then we have another multiplication, okay? So this is just a different model. And this model is called fully connected neural network, okay, FCN. Interestingly, we still use log likelihood function as our objective, okay? And there's nothing against that. It's still possible. And moreover, we will call this H as a hidden layer, and we'll call a single HM as a neuron, okay? So this is what people used to use, okay, as just a name. But we'll call them neurons, and that's why we call them neural networks. But these are fully connected neural networks because within one single layer from X to H, everything is connected. Every H is connected with X. And if we can, of course, stack even more hidden layers, right? We can put a lot of them, and it's perfectly fine. And so, importantly now is that we showed how we can stack multiple logistic regressions, but what are these basic components, right? It's a beautiful fact about neural networks is that they are modular, and we can basically define these basic blocks and then build from them very complex models. And so these components are linear layers. So by linear layer, we mean that we multiply X with some weight matrix. And by specifying one dimension of this weight matrix, we will define how many hidden neurons we have. Sometimes we can write it in this way, like W times X, or we can define it with an additional explicit bias. So this additional scalar B that shifts the whole vector A, the output. But very often we will just skip this B and we will just talk about linear layer in this way. Why? Because we can add value 1 to X, and this will correspond to learnable bias. And another part is nonlinearity. So here we talk about sigmoid, but of course we can use maybe other nonlinearities. So that's why we say that the final hidden neuron is a combination of nonlinearity applied after matrix multiplication in a linear layer. Okay. And what are typical nonlinearities? So first of all, sigmoid function. So this is what we know so far. It could be used either to represent probabilities or just to represent a hidden layer. Another nonlinearity is tanh. The difference between tanh and sigmoid is that tanh is between -1 and 1, and it is expressed by the sigmoid function. A big breakthrough in neural networks and in deep learning was when people proposed to use rectified linear unit, so-called ReLU. And this is a function that for positive part, it behaves like a linear operation, so it's just linear function. But for negative values, it returns 0. Okay, so it has a very nice property of sparsifying things. So the gradient is also sparse, and some people claim that this is extremely important. Another nonlinearity is softmax. And softmax is our we should be familiar with this concept. Is just to get probabilities for given axis element-wise. So we apply exponential function. We use it in having ranking selection for evolutionary algorithms. But here we have exponential of x divided by sum of all other exponentials. This gives us probabilities. So for every single given output, we'll have the output will sum to 1 basically, and this is good for cases when we classify to multiple classes. Okay. Right. Linear layer. Let's look at linear layers a little bit more. So linear layer is that we define a W, a weight matrix. It's a small mistake. It should be actually M times D. Sorry for that. Otherwise, it will be not properly defined. It's multiplication if X is d-dimensional. And importantly, we need to initialize somehow these weights, right? So there are 3 classic, there are more, but in literature, people use basically 3 initializations. So first is some Gaussian, so we initialize everything around 0 with very small variance. Another thing is so-called Xavier, from a name of a researcher who proposed it for tanh function. So we take the variance to be a square of 1 divided by d, where d is number of inputs, and he, so for ReLU, they realized that actually this is better to take square root of 2 divided by d. They provided some analysis why this is better, and indeed, in fact, in real applications, it matters quite a lot. So initializing your neural networks properly could lead to worse results. Okay, and of course another initialization is, for instance, uniform between -1 and 1 or something like 0.01, so small values uniformly. It's also possible. Okay. Activation functions. So in the first row, we have plots for sigmoid, tanh, and ReLU. And in the second row, we have gradients of this activation functions. So as you can see, the difference between sigmoid and tanh, so they are both so-called S-shaped functions, but the difference is that at tanh is between -1 and 1, and 0, it has value 0.0. There is nothing else. There are some like rescaled. And gradients are exactly the same, but again, tanh is 2 times sigmoid, right? So for 0, it will have, for tanh it will have 0.5, while for sigmoid it will be 0.25. For ReLU, this is actually very, very interesting, because for ReLU we have very peculiar gradient. It is 0 for negative values, and this is 1 for positive values. Okay, so this is like this this very, very peculiar property that gradients are very sparse. All right. So now let's discuss quickly how we deal with multiple classes. As you can see in maybe a general note, these slides, they are a little bit like we first introduced how to build a neural network by stacking logistic regressions. I believe that this is very nice, a nice way of thinking about neural networks. And now we talk a little bit how we can modify this, right? So we have these modules like linear layers, we have these non-linearities, we can change sigmoids to something else, but also we need to know how to deal with multiple classes, for instance. So because so far we talked about 2 classes and then we use sigmoid. To deal with k classes, we need to use softmax function. So now every single class will have own set of parameters, and we will just normalize it. Normalize this x of theta I times x. And of course, the probability distributions that we use, it's so-called categorical distributions, okay? Categorical distribution, a generalization of Bernoulli. And now, very important part is the backpropagation. This is the learning algorithm. So we know, let's say, that neural networks are stacked logistic regressors. We know that logistic regression could be learned by applying gradient descent. So how we can learn fully connected layers, networks? The question is, can we use stochastic gradient descent? And the answer is yes, because of the properties of gradients. So let's say that we consider one single hidden layer, right, with some non-linearities f. We can use the chain rule to calculate gradients with respect to all weights. How we can do that? So let's say that this L, this L looking like E a little bit, but this is L, is the loss function. What is the loss function? The negative log likelihood. So to calculate gradient with respect to U, we can apply, so let's say for a single weight somewhere, we just apply the chain rule. So we just need to rewrite this gradient to include the intermediate steps. Okay. This is the negative log likelihood, and of course, how to derive it a homework. This is a little bit a joke because I don't expect from you to derive it by yourself. So please take a look at it. Google for it, okay? Because it takes a little bit of time to do it, but it is I think pretty insightful if you do it by yourself. However, I repeat, this is not essential for us. In this course, this is non-pedagogical what I'm doing right now, but we will use a special package that will calculate gradients for us. But if you're interested in that, if you want to know a bit more, so please do it, please Google for it and check it out, okay? And one thing that it's very important to mention at this point is that, you know, it's really nice. Sigmoid is really nice. But if we look at this chain rule, right, so we define gradients also with respect to some functions, so nonlinearities and so on. The problem that could occur is something which is called a vanishing gradient problem. So this problem actually stopped the whole field of neural networks for a couple of years because people were unable to build truly deep models. And why? Because they encountered this vanishing gradient problem. And what is that? If we take a sigmoid nonlinearity, we know that we can calculate the sigmoid, derivative of the sigmoid function as sigmoid times 1 minus sigmoid. If our model is very certain, right, and this at some point or some neuron is very certain, at some point it will maybe give us sigmoid equal 1. What happens then? Then we'll have 1 minus 1, which gives 0, and the gradient with respect to this, with respect to s of this sigmoid function equals 0. So this is the vanishing gradient, because if one neuron is super certain, it will zero out a big part of neural network. It will be not trained at all. And then, for instance, we have, we calculate with respect to u, some neuron is 0, everything is 0, and this is a very bad situation, all right? Because a big part of neurons will be 0. And what will be affected the most? The first layers, because the first layers, they will be zeroed out, okay, very often. And what happened in the past is that people stacked 3 layers, they were able to train, they added another layer, 5th layer, and then it turned out that first layer was almost like a random, okay, randomly, like not far away from random initialization. So basically it was nothing, and the whole performance of the network dropped significantly. So this is for today. It went a bit quicker this time, but it's not bad. As you see, this is it is quite heavy, I would say, maybe for beginners. If you have never heard about neural networks, then please look at another time. Maybe you go through slides, try to understand everything, try to do it step by step. Personally, I really love this perspective of stacking logistic regressions as a beginning for understanding neural networks, and then realizing that we can create modules, some blocks, and from these blocks we can build fully connected networks. Another thing that is very interesting perspective is that a single neuron could be seen as a feature extractor, a single feature extractor from our data, okay? And that's why when we have one, maybe I can quickly show you. So what I mean by that, so when we have an image and we have, let's say, number 6, right? It could be a little bit something like thicker, right? One single neuron and of course let's change color. Say that we have some pixels. Of course, this is not perfectly fine because we should make it something like a lot of them. We have one single pixel here, right? So this neuron looks at the whole image, right? So it learns to look for some patterns. Okay. And so this edge will have own row of parameters, right? Then input, it's again, we can express this image, as a vector of the same size. What we are talking about, refresh, feature extractor. Okay. One single neuron as a feature extractor. So we multiply, of course, this with this, this with this, this with this, this with this, and so on, right? And what is interesting is that after all, because this one single row is of the same size as input space, right? After all, we can actually represent it. If this is the same size, we can express it as the same size as our image. And what is interesting is that these features, they will start learning some patterns. So for instance, this feature will learn to detect such circle. Another feature could detect, for instance, something like that. Another feature will detect something like that, for instance, right? It will be not perfect, but for instance, 3 hidden units, 3 neurons, they can maybe detect these 6 very well, and they will be very high probabilities or something very high values. So let's say that this H1 will be something like, for instance, we have sigmoids, almost 1, H2 will be something like 0.9, H3 will be 0.8, right? And others something like less. And so then this guy will say, hey, I see this pattern in this image. This guy, hey, I see this pattern. This one, I see this pattern, okay? So this is very interesting to also visualize in fully connected networks, to visualize weights. And if you train a neural network in this assignment, and if you visualize your weights of neurons, especially in the first layer, you can do it because you will have exactly the same size as your original image. You will see very interesting patterns, okay? And I highly recommend you to do it. All right, so this is another perspective, one perspective that we stack multiple logistic regressors. Another perspective is that we see a single hidden neuron as a single feature extractor that is trained automatically from data, okay? Of course, one thing is that what will be learned at higher levels? Well, at higher levels, we can see in some sense that we combine different neurons together, so different extractors. So by building a hierarchical model, we build something like patterns of patterns, okay? So this is how we can think about it. All right. I really finish here. Thank you very much for listening, and I hope that you enjoyed this lecture and you feel excited about deep learning neural networks, because we'll discuss next time how to implement neural networks, and at the last lecture we will delve into more details, more complicated architectures. Thank you very much.